approximation methods. This is called Riemann sums. And you'll interpret the area under a curve as a net accumulation of a rate of change. So you do have to be able to interpret what you got out of this. Okay, so on the first example, really this example is more of a how to set up the problems, and then we'll move away from that and go on in. So example, finding distance traveled with velocity varies. A particle starts, yes, that's a typo, starts at x equals 0 and moves along the x-axis with velocity via t squared for time t is greater than 0. Where is the particle at t equals 3? So at time 3, the question is where is it? So it's really, they're looking for the x value of which he's at, because this is a velocity graph, so it's going to give you time here. This is time, and over here is your velocity. Okay, so I'm setting this one up. I've done a lot of the work for you, but one of the things we need is the change in t, or delta t, which is going to be your stopping time minus your starting time all over the number of intervals that you're going to create on this. Now on this one here, we're going to do intervals of 12. We're going to do 12 intervals. So this would be 3 over 12 or 1/4. So that's our delta t. This is a guy that we need to pay attention to. So as we go through this, now I did start this up for you. Again, this is more to make space. Is that on this one here, we're starting at z 0. And so this is going to be 0 plus 1/4, because that's our delta t. And then our next interval will be where it stopped to the next one. So this becomes 1/4 plus delta t. So your starting point just follows over, and then this is your end point here. And continue on. 1/2 is your starting point. Then you go 1/2 plus delta t, which is 1/4. Gives you this one, and so on and so forth. So, and I know I was doing 1/4 and I changed delta t, so in the end this becomes 3/4 plus 1/4, which gives us 1. So I'm doing a midpoint, so this is called MRAM, midpoint rectangular approximation method, but it's also just called Riemann sums, so I need you guys to know what that word is. Well, we're doing the midpoint, and the midpoint between these two is 1/8. Since we're starting at 0 and going to 1/4, that one's an easy one to do. You just split 1/4 in half, gives you 1/8. Then to get to the next guy, again, guess what you're going to do? You're going to add delta t. So this guy here, 1/8 plus 1/4, which is 2/8, gives you 3/8. And then this would be 3/8 plus 2/8, which gives you 5/8, and so on. And then we go into, now keep in mind we're doing rectangles, and the area of a rectangle is length times width or base times height. In this case, we're going to do base times height. The base is going to be your t values, and the height is going to be whatever your function is. So there's our height, and it's just whatever the midpoint is squared, because it's x squared is our formula. So we take this guy and we square him. 1/64, 9/64, 25/64, 49/64. Now I am only doing the first 4 for you. And then to find the area of each rectangle, we now multiply it by the 1/4, what the width of each of those itty bitty little rectangles are. And so you get 1/256, 9/2, because we're just taking 64 times 4. The 9's not changing. And we continue on this way. Now there is another way that you can do this, is you can just add all of these up. So you can take 1/4 times the sum of all of the heights. You can always do that as well. By the way, this is indication for sum. So continue in this manner, derive the area 1/4 times the midpoint squared for each subinterval, and add them all up, and you get 8.98. There you go. If we were to throw this into the calculator, I believe we would end up, actually, I think we would get, I didn't put it in the calculator, I think we get something much closer to 9. I'm going to put it in the calculator because I just want to see what it is. We're going 0 to 3 of x squared. And according to the calculator, I would have gotten 9. So we got a very, very good approximation on this one. That we're basically at x equals t on the x-axis. They're saying on the x-axis, so we're really looking for a position here. So that's one of the things to keep in mind of what am I exactly looking for? I'm looking for where was x at when t equals 3. That was at 9, the x value of 9. That was its position. Okay, so now we're going to actually work through a problem. Most of the problems that you'll be asked to do, very seldomly they ask you to do anything beyond 10. It's usually going to be 4 or 5, maybe even 3. There's not a lot of purpose of doing only 2, unless you got something very symmetric and very square. Okay, so a particle starts, again, typo, at x equals 0 and moves along the x-axis with velocity v of t equals t squared plus 1 for time t greater than 0. Where is the particle t equals 4? Approximate the area under the curve using 4 rectangles of equal width and height determined by the midpoint of the interval. So they're telling you this a lot here. We have to use 4 rectangles and we need midpoints. Now, normally they would ask you to graph this and then to actually separate your 4, to actually show what the rectangles will look like. This will also allow you to know if you're going to get an over or under approximation on these. But we'll talk about those a little bit more here in just a minute as well. So if I'm wanting 4, so let's look at delta t is going to be 4 minus 0, ending time, starting time, ending time minus the starting time, divided by the number of rectangles. We're going to do 4. So 4 over 4 is going to give us 1. So delta t is just 1, which is not that. That's you. Yes, this is a nice number to work with. Okay, but we're going to still go through the whole thing. So our midpoint between 0 and 1 is going to be 1/2. And now to get to the next, by the way, on this one here, start at 0 plus 1, and then our ending point here is the beginning point here. 1 plus 1 is 2, so on and so forth. So this guy here was just 0 plus 1. This guy here was 1 plus 1. This one was 2 plus 1. And this one was 3 plus 1. And the starting point just came from the last ending point. That's all you got to do. Okay, and to get to this guy, I'm just going to take 1 and add 1/2 to it. Or you can do 2 plus 1 divided by 2, which is going to give you 3/2. 3 plus 2 divided by 2, 5/2. 4 plus 3 is 7, divided by 2, 7/2. Now this one I have wrong, so let's fix this. This should be midpoint squared plus 1, because that's the velocity function, t squared plus 1. So midpoint squared plus 1. So I'm going to square this, which is going to give me 1/4. So this is going to be 1 over 4 plus 1, or 5 over 4. And I continue doing. Square this guy here. I'm going to get 9 over 4 plus 1. By the way, for those of you who are scared of fractions, whenever you're adding 1, just add your numerator and denominator together. 9 plus 4 is 13, so you can get 13 over 4. This one is going to give us 25 over 4 plus 1, so I'm going to get 29 over 4. And then this one is going to give me 49 over 4 plus 1, or 53 over 4. So the area, let's fix that one too, because I made a mistake on that one as well. This is going to be the midpoint squared plus 1, because that was the formula, times 1. This guy here is this is your base, the width of your base, and this is your height. But we're multiplying by 1, so it's just all of these values coming down. 5 over 4, 13 over 4, 29 over 4, and 53 over 4. And then you add them all up. Since my denominators are the same, I'm just going to add them up. So to get this value, I get 5 plus 13 plus 29 plus 53, all of this mess over 4. And in the end, I'm going to get 100 over 4 or 25. So this is our x value. The position on the x-axis is 25. That's where I'm at. Okay. So from there, what we can do is talk about what's happening with this one here. Now, the very, very first problem we did was the midpoint. We did the midpoint for y equals x squared from 0 to 3. So we come down here, and when I do the left midpoint, I'm grabbing all of my left values. And this is what I'm saying, that a lot of times they'll ask you to graph. And you can see that there's a lot of information that is not being accounted for. And therefore, we are getting in under, because I can also continue this line up here too. This is an underestimation. This one being the midpoint, and you can see that it's going through the midpoint of each of these, is that this one is going to be most accurate right now, because you'll see it's a little bit on above the line and a little bit below, a little bit above, a little bit below, a little bit above, a little bit below. This is really hard down here to do. A little bit above, a little bit below, a little bit above, and a little bit below. So you can see that they kind of counteract each other. And so that's why a lot of times they'll tell you to do midpoint, because you're going to get the more accurate answer there. And so this was the left Riemann sum. This is your midpoint. And this is your right. Now, here's the one thing. I can't say you're going to go, oh, I'm going to do midpoint because it's most accurate. A lot of times they will simply ask you to do one of the others so that you can, just to see that you know how to do them. So don't go, oh, I'm going to just know how to do this one and I'm not going to do anything else. No, don't do that. Okay, but this one here, this one's going to be that underestimation, because you've got a lot of information that is not under the curve. Oh, not under, sorry, over. I wrote that, I'm going, something's not right. But you have a lot of this information that's above the curve, but you're counting those values. And so this is why you're going to get an overestimation more times on the Riemann sum. Now keep in mind also that this guy here is concave up. So the question would be, is what would happen if these were concave down? Would it go the other way? You know, what if my graph from here, instead of being concave up, did a concave down? Did it concave down? Did it concave down? The question, would we get the same results? Here's what I want to do, is show you what's going to happen as the subintervals increase. Now we did this one, and we did the midpoint one, and this is what we, oh, sorry, we did it at 12. This is the one we did, and we did it at 12. And you can see the left is very much an underestimation, and the right is very much an overestimation, especially now that we know the answer is 9. And I did that earlier. But notice as we get closer and get more and more, as our n value approaches infinity. So yes, let's talk about limits. Limit as n approaches infinity. I round this baby, I'm going to get 9. I round this baby, I'm going to get 9. I round this baby, I'm going to get 9. Even these guys. You know, you're going to go through a lot of these ones, but you know, at 24, I'm not going to get 9 here or here. But even at 48, we're already starting to get our values much, much closer to 9. Much, much closer to 9. And remember, calculus, they want 3 decimal places. So this would still be 8.721. This would be 9. And this would be 9.283. 3 decimal places here, 8.865. This one would round to 9. And this one would be 9.135. But what about this one's 3 decimal places? This 5 would make this 6, so 987. this is definitely going to round to 9, and this is 9.013 or 9.014. You can definitely tell we're getting closer and closer and closer to that value of 9. So what would happen if we did 10,000? We're not going to do those. I'm just going to let you guys know. We're not doing those. I just want you guys to see what's going on here. Okay. So this is where I'm thinking about leaving off. It's giving you the first opportunity to really work through something. I think I will go ahead and cut this off here. We've got more to do, but we'll cut this one off here. So go ahead and start working on some of the problems, some of the basic ones that just ask you for the left-right Riemann sums, and we'll talk more on this tomorrow. Good luck.